A type 1 error occurs in statistical hypothesis testing when a researcher rejects a null hypothesis that is actually true. The null hypothesis is a statement that assumes there is no effect or no difference in the data being tested. Rejecting it implies that the researcher believes there is evidence for an effect or difference, even though this conclusion is incorrect. In simpler terms, a type 1 error is a false positive, a result that mistakenly indicates that a significant effect exists when it actually does not. The probability of making a type 1 error is denoted by alpha, often set at 0.05 or 5%, meaning there is a 5% chance of wrongly rejecting a true null hypothesis. Type 1 errors arise due to the inherent uncertainty in statistical testing. When researchers analyze data, they rely on sample information to make inferences about a larger population. However, no matter how carefully the study is designed, randomness can lead to results that look significant by chance alone. For example, if a researcher sets alpha at 0.05, they are willing to accept a 5% risk of concluding there is an effect when there is none. This threshold helps balance the trade-off between sensitivity and precision, but it cannot eliminate the possibility of error entirely. Type 1 errors are particularly problematic because they may lead to false claims or misguided actions based on incorrect conclusions. Another factor contributing to type 1 errors is multiple testing or comparisons. When researchers test many hypotheses simultaneously, the chances of encountering at least one false positive increase. To address this, statistical methods such as the Bonferroni correction adjust the significance level to reduce the likelihood of type 1 errors in multiple tests. While these adjustments lower the risk of false positives, they also make it harder to detect true effects, illustrating the delicate balance in statistical testing. Now let's look at some examples of type 1 errors. Imagine a medical researcher testing a new drug to reduce blood pressure. The null hypothesis states that the drug has no effect on blood pressure compared to a placebo. After analysing the data, the researcher finds a statistically significant result and concludes the drug works. However, in reality, the drug does not actually lower blood pressure. This false conclusion is a type 1 error, leading to wasted resources and possibly putting patients at risk if the drug is marketed based on this incorrect finding. In another example, consider a quality control manager at a factory. The null hypothesis might be that a machine is functioning correctly, producing products within acceptable standards. If the manager's statistical test rejects this hypothesis based on random variations in the sample, they might unnecessarily shut down the machine for maintenance. This type 1 error could lead to lost productivity and unnecessary costs. Lastly, in an academic setting, a researcher studying the effects of a teaching method might conclude it improves student performance when it does not. This type 1 error could lead to the implementation of an ineffective teaching strategy, misallocation of resources, and confusion about what truly benefits students. Type 1 errors underscore the importance of careful statistical design and interpretation. While they can never be entirely eliminated, researchers can reduce their likelihood by choosing appropriate significance levels, using corrections for multiple testing, and interpreting results in the context of broader evidence. Recognizing the potential for type 1 errors reminds us to approach scientific conclusions cautiously, valuing both rigor and replication in the pursuit of reliable knowledge.